This is an introduction to the Fourier series. First, let's look at the graph of the sine x and sine 2x and all that. As you can see, if this number in front of x, which we call the angular frequency of the trig function, if this number increases, then the number of period that fits inside the negative pi to pi is increased. So right now this is 2, and you can see now we have 1 and 2 waves inside from negative pi to pi. And this, if this is 3, then it'll be like 1, 2, and 3 inside negative pi to pi. Now, as you can see in the graph, whatever this number in front of x is, whatever the angular frequency is, the amount of the graph that's above the x-axis and below the x-axis is the same. So here we have above and below, same amount, right? And that goes the exact same way for the cosine. This is 1 period of cosine, this is 2 period of cosine 2x, and again the number of periods of the trig function is determined by what number this is in front of x. Okay, this is talking about the graph from negative pi to pi. And again, if you look at the amount of part that's above x and below x, it's the same amount. Right? What does that mean? That means that if you integrate these sine nx functions or cosine nx, whatever n is, it always integrates to 0. Okay, so that's the first established fact. Although you could actually just check that's true. I just wanted to show you a graphical way of seeing it. Here's the product of sine x and cosine x. If you multiply sine x times cosine x, you get this graph, which is just another sinusoidal function. And you can see that this is somewhat like the sine with 2 periods, so it may have something to do with sine 2x, right? Indeed, there's a trigonometric identity which says sine x times cosine x is equal to 1/2 of sine 2x. But you don't need to know that. Let's say this, let's say we just drew this using a graphing calculator. This is what we get. Now, if you had y equals to sine 2x times cosine 7x, then you get this complicated waveform, and it's hard to track what's happening, but you do see that there's some kind of symmetry of left and right? So on the starting from the origin, as you go right, you go up and then down, but if you go left, you go down and then up. And then you can see that the amount that you go up is same as the amount that you go down, whether if you compare going to right and going to left. And graphs with such symmetry is called an odd function. We know that it's an odd function in this case when you have a sine function and cosine multiplied together, because we know that if you have an odd function and an even function, it always results in odd functions. Okay, since you may not know what an odd function is or an even function is, let me try to explain what they are. Okay, first, what's an even function? Even function is a function such that is symmetric over the y-axis. So imagine you have y equal to cosine x graph, and if you folded this graph along the y-axis, you can see that the right side and the left side match evenly, right? And other functions that have such properties are, for example, y equal to x squared, y equals to x to the 4th minus x squared. They both have these graphs that fold evenly if you fold it along the y-axis. Now, this has some important consequences in terms of the integral. If you integrate from negative pi to pi of such a function, then it is same as doubling the integral from 0 to pi of the function, because just integrating the right side, it will be the same as integrating the left side. So instead of integrating everything, why not just integrate the right side and double it? Now in practice, you will find that plugging in 0 is much easier to calculate than plugging in negative pi when you use the fundamental theorem of algebra. So although this may not look like a big deal, but in practice this will be a real time saver. Okay, now the odd functions, symmetric over the origin. So odd functions are what we call symmetric over the origin. As I said earlier, if it goes up as you go right, it should go down as you go left. If it goes down as you go right, it should go up as you go left. And some examples of such functions are shown here. Now, for the integral of the odd function, it's even easier to know, because if you integrate an odd function over a symmetric domain from negative of a to positive of a, then you get a 0. Why is that? Because if one side is positive integral, the other side is negative integral, and their values match, so they cancel exactly. So integral of the right side is same as the integral of the left side, but with a negative sign. So when you add them up, you get 0. So it's very convenient to integrate the odd functions. Now, there's a way to figure out whether your function is an odd function or an even function. You have these nice thing that always works. If you have two even functions and you add them up, you get an even function. If you add two odd functions, then you get an odd function. If you add an even function with an odd function, you don't get anything. Actually, most functions that we know do not have either of the symmetry. It's neither even or odd. So, for example, exponential of x, that is neither even or odd. Most polynomials you write, it won't be even or odd. Okay. But if you have two even functions, then if you add them, it's an even function. And then there are other formulas, as you can see here. Now, rather than memorizing these, it is better to remember the examples. See, x to the n with even power is an even function. X to the n with odd power is an odd function. That's where the name even function and odd function came from. And if you take x squared, which is an even function, and multiply by x cubed, which is an odd function, you get x to the fifth power, which is an odd function, isn't it? And therefore, you have seen an example of the fact that an even function times an odd function is an odd function. Now, in addition, think about the Taylor series of the cosine. Cosine's Taylor function starts with 1 and then minus 1/2 x squared plus 1 over 24 x to the fourth, and so on, right? So if you look at the Taylor series of cosine and sine, you can see that the Taylor series of cosine has only even power terms, and the Taylor series of sine has only odd power terms. And that's another way to see why cosine and sines are even and odd individually in each case. Product of sine and cosine. So back to product of sine and cosine, we've established that it's an odd function, and therefore the integral is 0. Very simple, right? Now, we need to know more integrals in order to understand Fourier series. The next topic is product of sine and sine. How do you integrate the product of sine and sine? For example, if you have product of sine 3x and sine 8x, this is the graph. It's very complicated, and you can see that, well, you can't see from the graph. If you can prove that if you integrate this, you get 0, as long as the n and m are different. Now, why is that? The reason is not so obvious, so we have to do some very hard trigonometry here. There's a trigonometric identity which says sine nx times sine mx is negative 1/2 cosine n plus mx minus cosine n minus mx. And then if you use this, then you get this straight up answer, which is just 0. That's because we've already established that if you integrate the cosine by itself, it's 0. However, this integral is misleading in the case when n is equal to m, because if n is equal to m, you get cosine of 0. Cosine of 0 is 1. It's a constant function, not a trig function. Therefore, when n is equal to m, then the integral has the value of pi, because if you integrate 1 from negative pi to pi, that's the length of the interval, which is 2 pi. Dividing by 2, it's pi. Now similarly, if you have cosine times cosine, you can use this identity and then get the following conclusion. If m and n are distinct, it's 0, but if m and n are equal, then this integral turns into pi, so the integral is pi. So here are the summary of all the trig integrals that we discussed so far. And these integral values, these integral results are called orthogonal relations, because there is some higher mathematics that you may be able to learn in grad school that says if you have these product of functions integrated over an interval, you can think of them as dot products, where your function space is like the vector space. But you don't really need to know all that here. We will just focus on the fact that you have these orthogonality relations. Alright, so what are these good for? The answer is that it's used for Fourier series. So now let's look at what a Fourier series is. What's a Fourier series? A Fourier series is a way of approximating functions using sine and cosine functions. And here's an example. You have y equal to x squared. And then if you draw the graph of y equals to pi squared over 3 minus 4 cosine x, then you have the following graph, this purple graph here, which is very close to the graph of y equals to x squared. Now you may not be so impressed because of the shape of the graph doesn't look anything like y equals to x squared. So let me impress you by introducing another series of cosine functions that mimic the y equal to x squared pretty well. So here is the function. It's rather complicated, but it uses cosine x, cosine 2x, cosine 3x, cosine 4x in some way, and a constant function to mimic this y equal to x squared in an impressive way. I mean, isn't it very close? Especially down here, it's almost the same. Here's another example. If you have the sum of sine x, sine 3x, sine 5x, and sine 7x with these weird coefficients, then you can see that the graph mimics this step function. This step function takes the value of -1 before 0 and 1 after 0. So what we are trying to do is that suppose you're given this function. The question is, what trig functions mimic this function as much as possible? And the answer that we come up here is that sine x and sine 3x, sine 5x, sine 7x added up in this way will produce something similar to the step function. Again, you might not be impressed, so let me show you something much larger. So here's a sum of sine odd number times x, sine 3x, sine 5x, and all the way up to sine 101x with some strange coefficients, which adds up to produce this purple graph, which is very close to the step function that's given to us, right? So this is what we call the Fourier series. Fourier series is actually an infinite series that if you add them up until this if you add up infinite number of trig functions, you end up with a function which is exactly same as the given function, except in a few points. Maybe a few points it might be different, but except for a few points, it's exactly the same. Now, how do we get these coefficients? That will be the question, right? You may be convinced so far that you can talk about a Fourier series of any given function, but in order to actually have a useful theory, you need to know how to get those coefficients, right? So here is another approach that we're going to take. Let's say our function is a sum of sines and cosines. It's an infinite series, okay? And we're trying to mimic a given function by choosing appropriate coefficients. We have to determine these coefficients, a0, a1, b1, a2, b2, and all that. What we're going to do is that we're going to multiply the cosine both sides. Actually, let's just say that we know all the values of the function f of x, but we don't know these coefficients a0, a1, b1, and a2, okay? Now, how can we find out these coefficients? That's what we are aiming for. So here, multiply the cosine x both sides, and let's integrate. Just simply integrate. Okay, so let's see. So as you can see, I had the function before, and now we multiply cosine x both sides, and then we integrate. Now, do you recognize these integrals? These are integrals that we've done before, and we know their values because of the orthogonal relations. We know actually that most of these are 0. This is 0, this is 0, this is 0, and this is 0. The only non-zero thing is cosine times cosine, because it's cosine 1x times cosine 1x, so m and n are equal, right? So here's the orthogonal relations that we've done before. See, when n and m are equal, then it produces pi, otherwise it's 0. Right? So back to our integral, we know that all of these red cross things are 0, and the only thing that's non-zero is this integral, which gives you pi, and therefore we see that we have a nice formula which says pi times a1 is equal to the integral of fx times cosine x. What does this mean? It means that a1 can be obtained by performing this integral, 1 over pi times the integral from negative pi to pi of fx times cosine x dx. Now, because I said the values of the functions are known, we can certainly integrate this function, and then if you multiply 1 over pi, then we will figure out that unknown a1. Now, if we did this process with cosine 2x being multiplied, then the identity will be this one. And if you wanted a3, of course, this would be cosine 3x. a4, you would multiply cosine 4x. Now, repeating this process for a and also b, we can draw the following conclusion. If you set the function f of x as this, then we have a nice formula for finding a(n) and b(n) by these integrals. Okay. So here's an example. Suppose you have f of x equals x squared. Now you can integrate this with respect to cosine nx, and then by doing integration by parts, we end up with the following conclusion. Now, one thing that you have to know is that this computation is only valid for n equals to 1 or greater, because see, we are dividing by n here, right? And that's not good if n is equal to 0. In fact, when n is equal to 0, it's no longer a trigonometric integration. It's just cosine 0, which is 1, and therefore you have just the integral of x squared. So that has to be done separately. And this is something that you have to be careful when you compute ANs. Now, one handy formula that you have to know is that cosine nx and cosine n pi is equal to -1 to the nth power. It's going to show up frequently enough that you should also remember this. Also, sine of n pi is equal to 0. That's another really important fact. So, let's compute this. We only did an, right? Now let's do a0. A0 is just this simple integral which gives you 2 pi squared over 3. And for bn, it's very easy because x squared is even function and sine nx is an odd function. So when you multiply them and you integrate, you get 0 because of the fact that it's an odd function. Now, using these values, 4 over n squared times -1 to the nth power, and also 2 pi squared over 3, you can get the Fourier series, which is actually the Fourier series that we've obtained before. See, these numbers were obtained by using those formula. Let's compare the Taylor series with the Fourier series. Taylor series uses polynomials to approximate, right? It's an infinite series, whereas Fourier series uses sines, cosines, and uses trig functions. Now, Taylor series uses derivatives to find the coefficients, while Fourier series, the formula for finding coefficients, requires integration. Taylor series requires the function to be differentiable, of course, because in order to differentiate, the function has to be differentiable, right? But Fourier series, because you just have to integrate, it doesn't have to be differentiable. Actually, this is one of the reasons why people like Fourier series. Taylor series gives good approximation in a small interval near the center of expansion, whereas Fourier series gives good overall approximation in the interval, minimizing the area between the approximation and the target function. Since sine and cosine are continuous, you can see that when the function has a jump, there is this thing called the Gibbs Phenomena that happens near these jumps. So here the purple graph is the Fourier series that tries to mimic our black graph, which is a step function. And as you can see, away from that jump, the Fourier series, the truncated Fourier series, does a pretty good job in approximating the function. However, whenever there is a jump, it has this thing called the Gibbs Phenomena. Actually, one of the places that people use Fourier series is in computer multimedia. Popular graphics format is JPG or JPEG, right? That uses Fourier series to compress images. Also, your MP3 files, they're making use of the Fourier series. Now, how do these work? Well, imagine your music as complex waveforms, which is just a function, right? What MP3 players do is that it truncates the given waveform, and it takes the Fourier series of that waveform, and then it records only those coefficients. And in most cases, just recording a few terms of the coefficients is good enough to mimic that complex waveform. However, these MP3 formats and also JPEG formats, they suffer when the given waveform has clips, meaning high jumps. If it jumps from one place to other very fast, in a very in an abrupt way, then it's going to suffer because of this Gibbs phenomena. And for graphics, those things happen when you have edges of an object. And if you magnify a JPG file picture, then you can see that near the edges of objects there are some kind of artifacts that's wave-like, like this, and that's because of the Gibbs phenomena. Same thing with the MP3 files. If you have a highly percussive, or maybe rock and roll with lots of drums, the bass drums and snare drums, those have very high changes, because when you hit an object, there's a very high change in the waveform. And there are the cases when, because of the Gibbs phenomena, the sound quality is not so great. So whenever you're trying to compress using MP3 of rock and roll music, then you should use higher bit rate, because the sound quality won't be that good. Okay, back to Fourier series. Here's a Fourier approximation of the given graph, the previous graph, over the interval negative 2 pi to 2 pi. So we're drawing this graph from negative 2 pi to 2 pi. Now, do you see something strange? Inside the window that we were trying to approximate, it was doing exactly what we thought it would do, but then outside it goes down again, right? Why is that? Well, that's because these functions are periodic functions, and if you had periodic functions, you add them up, then the entire thing will still be periodic with respect to the biggest period. This is assuming that all the other functions have periods which are integer divisions of the largest interval. Okay, so if you add them up, this function has a period of 2 pi, so whatever you have here will be repeated again, left and also to the right. So it's like taking this graph and Control-C, meaning copy, and then Control-V, Control-V, Control-V to the right, and Control-V, Control-V, Control-V to the left. That's what the graph of this function would do if you drew it in a larger interval. Now, that kind of explains why on the previous graph you had the Gibbs phenomena on this left side and the right side, because see, in the eyes of the Fourier series, you're really trying to approximate a function that's periodic. So if you're given this function, there's a jump here, but there's also another hidden jump here, because it has to go from here and come back to this place, so it's a hidden jump here. So in both cases you have Gibbs phenomena. So an important thing to know is that if a function is defined over the interval negative pi to pi, and you're trying to approximate by Fourier series, it's really trying to approximate the function by a periodic extension of f of x. Okay, let's do another example. Here, f of x is given as x, and let's try to approximate this function from negative pi to pi. Now, remember, when we're trying to approximate this function, we're really thinking of this function as a periodic function. Right? See, the function given to us is only defined from negative pi to pi, and we're free to say whatever the value of the function is outside this negative pi to pi, and let's just say it's like this one. Okay, what's the Fourier approximation of this? Well, to do that, we have to do the integral, right? So let's do these integral. This time an is easy, it's always 0, because it's a product of an odd function times an even function, which is an odd function, so it's always 0. But for bn, we have to do this integration by parts, which gives you negative 2 over n times negative 1 to the nth power. And therefore, if you write down the Fourier series, you end up with this f of x equals to 2 times sine x and all that. Now, if you truncate this function at the 7th term, you can see that you have these purple graphs, which tries to mimic the given function. Again, you can see the Gibbs phenomena whenever there's a jump. If you truncate this at the 15th term, it's even more impressive, right? It's from, except for these jumps, it's almost same as the given graph. Now, so far we've done only functions given from negative pi to pi. what if we want to approximate a function in some interval negative L to L? Well, in that case, we have to use the following modified form. And this can also be proven by calculating the orthogonal relations for negative L to L with these trig functions, which is cosine n pi x over L. Okay, we will do further examples of these later.